Hi and hello, I am Athena Pondian here. Welcome to the Basics of Biomedical classroom once again. Today we are going to see the next topic of the first unit, that is we already crossed over the resistor and capacitor. Now we are going to see the next basic element that is called as the inductor. So what is inductor and what is the use of it and how we can able to use that in the way of simple notation and the diagrammatic notation, and what are the types of inductor is there or not, all the thing we are going to discuss under this particular topic, inductor. Come, let me start the class now. The topic is inductor. Inductor. It is a passive electronic component. Consecutively, we are seeing the third passive element, because the resistor and capacitor is also coming under the passive electronic component. What is passive? Already we know that it does not give any energy. It does not give any energy in the way of power or current or voltage. Here it can able to store the energy, okay, or it can able to dissipate the energy. That is the main job of the passive electronic component. So as this particular inductor is also a passive electronic component. The diagrammatic notation of the inductor is like this, and the alphabetical notation is capital L. So this is the induction alphabetical notation and the diagrammatic notation. This is a two-terminal passive electronic element. It can't able to give energy, it can able to store the energy. That is the main brief introduction about this inductors. This particular inductor is also called coil or choke or reactor. Why it is called as a coil is basically this particular inductor is wound like a wire in the core. For example, if you place a core like this, if you can able to wound over this particular wire here, there is inductor here, it will create some of the magnetic field, because this inductor having the capacity, this inductor is purposely used for storing the electrical energy in the magnetic field. Okay, that is the very important purpose of this inductor. It can able to store the electrical energy. But if this particular inductor, it has wounded over the coil, then that having the capability to create the magnetic field around it, magnetic field around it. So many of the purpose this particular inductor is useful. Especially, can I take an example of the some of the MRI, some of the basic MRI prototype. We can able to because MRI needs a magnetic field. For the prototype purpose, if you want to do the projector for the prototype of the MRI, we can able to use this inductor for creating the magnetic field over there. So that is the very important thing. The purpose of inductor is storing the energy in the form of electrical energy, especially in the magnetic field. Okay, what is the unit of this particular inductor? Of course, as a resistor and a capacitor, they are having some of the resistance value, that is called as an ohm, and a capacitor, we are having a capacitance value that is measured in a farad. As that, inductor is also measured in the way of inductance. The unit of this inductance is Henry. Most importantly, very important, unit of inductance is Henry. Inductance is the measurement value of the inductor. So this particular Henry can able to define as, it is the ratio of the induced voltage. It is the ratio of the induced voltage to the rate of change of current causing it. That is very important thing. Okay, please remember, what is inductance is nothing but inductance is the value for the any sort of the inductor. That inductance can be defined as the ratio of the induced voltage to the rate of change of current causing it. Because especially we are talking about this particular inductor in the magnetic field, it can able to create a core like a magnetic field over the if you are placing the coil over the core, then we can able to create the magnetic field in around it. That is why we can able to fix inductor, we can able to measure the inductance in the Henry. Because of the measurement of the inductance in the Henry, the ratio of the induced voltage, because of the induced voltage only the current will passing through this particular inductor. Because of this particular inductor is coiled over in this particular core, the magnetic field is created around it. So that is what the rate of change of current causing it, because of the voltage. Because of the induced voltage, the rate of change of current causing in that particular area. So that is why we are fixing Henry as a unit of inductance. Okay, that is a very important thing.
Generally speaking, an inductor is a device that temporarily stores energy in the form of a magnetic field. Inductors are usually just coils of wire, and one of the basic properties of electromagnetism is that when you have current flowing through a wire, you'll create a small magnetic field around it. So if you coil up a lot of wire, you'll get a stronger magnetic field. When current first starts to flow through the coil, a magnetic field starts to expand, then stabilizes, and then you've got some energy stored in the magnetic field. When current stops flowing, the magnetic field starts to collapse, and the magnetic energy gets turned back into electrical energy. So they're kind of like a temporary storage area for energy. You know how capacitors store energy in the form of a static charge and resist sudden changes in voltage? Well, inductors are very similar. They store energy in the form of a magnetic field and resist sudden changes in current. And if you only learn one thing from this video, remember, the current in an inductor cannot instantly change. It always lags by a certain amount of time. Now let me give you an example. Normally when you connect a voltage source to a load resistor, the current will be given by Ohm's law. In this case, 10 volts divided by 20 ohms gives you half an amp. And for this demo, I'm going to be using a 50% duty cycle square wave, so half the time you'll get 0.5 amps flowing, and half the time there'll be no current flowing. Okay, so here's the 1 kHz input square wave. And here's the current waveform, also perfectly square. Now watch what happens when I add a 5 millihenry inductor in series with the circuit. All of a sudden the square wave isn't so square anymore. There's a little bit of lag in the current. And this is because it takes a certain amount of time to store and release the energy in an inductor. Now let's try that again with a higher input frequency of 10 kHz. Now it's even more obvious that the inductor is impeding the sudden changes in current. This happens more and more as I raise the frequency of the input wave. At 100 kHz, there is no square wave anymore. It takes a longer time to store and release the energy in the inductor than the time it takes for the input wave to switch from high to low. So in this situation, the inductor is starting to average out the current over time. And this is very useful. It forms the basis of LC low-pass filters, which I'll cover in another video. But just to give you a quick example, if I add a 1000 microfarad capacitor just after the inductor here, I get a very clean DC output from a square wave input. And this is what good power supplies use to smooth out voltage. And to prove to you that all this happens because of expanding and collapsing magnetic fields, I'm going to feed a square wave into this unshielded inductor here. And I'm going to use another inductor as a magnetic probe, so I can view any magnetic field changes on the oscilloscope. On top I have the input wave, and on the bottom you can see the magnetic field that I'm picking up as I get closer to the inductor. Finally, inductors have almost no effect on DC. They're basically just pieces of wire with a resistance of a few milliohms.
Is a coil of wire wrapped around a magnetic material. Current flowing through the inductor creates a magnetic field, and magnetic fields do not like to change. As a result, an inductor is a device which tries to prevent the current flowing through it from changing. If the amount of current flowing through the inductor is constant, the inductor will be happy and it will not generate any forces on the charged particles flowing through it. In this case, the inductor behaves just like a normal wire. On the other hand, if we try to interrupt the current flowing through the inductor will generate a force, trying to keep the current flowing through it. If an inductor is connected to itself and there is no resistance in the circuit, the current will theoretically continue circulating forever. However, unless we are using superconductors, all wires have some resistance to them, and the current will eventually decay to zero. The larger the resistance, the faster the current will decay. But the larger the inductance of the inductor, the slower the current will decay. Once the current is at zero, the inductor will want to keep the current at zero, due to the fact that an inductor tries to prevent the current flowing through it from changing. Therefore, when we connect this inductor to a circuit, the inductor will initially create a force trying to prevent the current through it from increasing. But the current will slowly increase. The larger the inductance of the inductor, the slower the increase in current will be. After the current has stopped increasing and has reached a steady value, the inductor will then again be happy and not generate any forces. But when we try to turn off the current flowing through the inductor will then generate a force to try to keep the current flowing through it at this new constant value. If the inductor is then connected to a resistor, the voltage across the resistor will be the current multiplied by the resistor's resistance. The inductor prevents the current flowing through it from changing instantaneously. Therefore, the current flowing through the inductor immediately after we flip the switch will be exactly equal to what the current was before we flipped the switch, regardless of what the value of the resistor is. If the value of the resistor is extremely large, then the current multiplied by the resistance will also be extremely large. As a result, inductors can generate extremely high voltages, at least for a brief period of time. Since the current through an inductor cannot change instantaneously, when we try to disconnect an inductor from a circuit, we always need to provide a path for the inductor's current to flow. If we do not provide a path, the inductor's current will find its own path, such as through the air, through the open switch, or through other components that are not supposed to be conducting electricity. This can create very large voltages and cause considerable damage to the circuit. The ability of an inductor to create large voltages makes them very useful in the design of power supplies. But this ability also means that care must be taken to ensure that we never try to switch off an inductor without providing a path for its current to flow in.
That particular basics of the inductance video will help you a lot to know about, remember about what is the inductance and what is the basics circuit needed the inductance and what is the role of that particular inductor in the basic circuit, all the things we know that. So that's all about this particular inductance video. In the next class we are going to see one of the basic important electronic component, that is transformer. Thank you very much.